So what I'm going to start with is, I don't want to call it a test, but what I'm going to do is I'm going to show you two different images. And what I want you to do is, when you see an image, just tell me what you think it is. Now, if you're shy, you can say it in your head, or you can shout it out loud, but just tell me what you think what I show you is. Okay. So, driver's license. Okay, thank you, Cantor. Yes, this is a driver's license. This is my driver's license. And I'm going to do one more test. So once again, just feel free to shout out what you think this is. The business card. Okay, so we all did that pretty well. Now this third item, I'm not going to show you. I want instead for you to think in your mind what a 1960s era Soviet military ID would look like. Now just picture, take a moment, picture in your head, think what that would look like. I'm assuming none of you were in the military in the 60s in the Soviet Union, so probably none of you have seen one, and certainly have not been asked this request. So just put it somewhere in your head, and we'll come back to it later. So the question is, how did we all get this? I'm sure some of us would have jumped in quicker if it wasn't a public speaking forum, but the idea is we can try to track through our thinking. Well, an obvious answer is, well, the one on the left says driver's license, so that's a slam dunk. But the business card doesn't actually say business or card. And also, if you give people this task, they can do it much more quickly than you know that they can do if they're actually reading the card. And so what's happening is, this is a classic perception task. And the reason this is so fast is because in our evolutionary history, different animal species needed to very quickly identify some object in the distance, classify it correctly, and pass that information along so that they can know what to do about it. If it's a predator, if it's a prey. And our brain still has all of these pathways, and those get applied in different ways. And so what's really happening is, our brain is a working model, a working perception model of what an identification card looks like, what a driver's license looks like. And what it's actually doing is running a bunch of different small subtasks, like edge detection and facial detection. And the same thing goes for the business card. So if we threw a whole bunch of playing cards and credit cards and business cards on the floor and gave any one of you the task of picking out the business cards, it would be trivially easy, and you would all do it with a very high degree of success. And this is one of the powers of perceptive tasks. But I'm going to switch gears and start talking about what a cognitive task is. So I will highlight two parts of the screen. So you can see I've highlighted Colorado, and I've highlighted British Columbia. Now, depending on your familiarity with North American geography, these two highlighted portions of the cards may seem familiar to you, and they may seem similar. So the question is, why is that? Well, Colorado is a larger font, it's a different font, it's in a different part of the card. British Columbia is two words, and the words don't sound anything like each other. It's not like shake and bake. And then I can tell you more information. I can say Colorado is a state in the United States. British Columbia is a province in Canada. Again, those sentences don't sound like each other. So why are these very similar concepts? Well, it's because your brain has a working knowledge model of how places in the world are organized. You know that the land in the world is owned by countries. Countries are subdivided into smaller units called states or provinces or territories or other words. And that you know in the hierarchy of these concepts that underneath the United States, Colorado is a state, and underneath Canada, British Columbia is a province. So within these relative hierarchies, they actually have similar positions. So they feel similar. But the idea is you can't extract that relationship from these two images alone. So if I were to have instead highlighted license and section, or license and geology, the same effect doesn't occur. And the idea is that in order for you to explain why they're similar, you actually engage in a mental task. You have to think. Now, you might identify them quickly, but in order to explain it, you have to engage in this mental action. If I were to ask you all how you knew it was a business card, you could give me a bunch of reasons. But more than likely, you'd be coming up with sort of a post hoc explanation, when in reality, it's a subconscious perceptive process that is effectively a black box to you. Your brain knew what it was far before you could have explained it. So to take that over to the geosciences, we've all probably heard about different artificial intelligence techniques being used in the mining industry. And to date, most of them have actually been these perceptive tasks. So machine learning is a type of artificial intelligence that people have probably heard. And the idea is that a lot of the great successes in mining have come from these perception tasks. Things like autonomous haul truck driving, process optimization, predictive maintenance for vehicles. And the reasons these are so successful is because you have a lot of data in a mine, you have a lot of continuous data, you have control over the data, and most of the data tends to be more objective. It's hard numbers and RPMs of the engine and the ambient temperature when the haul truck broke down. But the most important thing is, when people are targeting these tasks, they have very clear indicators of success and failure. If you adopt a autonomous haul truck driving program and it crashes, that's a clear failure. If you have 960 consecutive run days without a failure, and the best human operators streak was 603, well, that's a clear marker of success. And so it's been really, really fantastic to see all of these different techniques utilized in the mining industry. But the problem is that not all of the tasks that we run into as geologists and miners and engineers are suited to a perception style of process. And so one of those is mineral exploration, and another one would be something like tailings dam safety or catastrophic events. So why are those problematic? Well, one of the main issues is number of training examples and types. And so if you look at mineral deposits, unlike evaluating 1,000 days of a haul truck's success, you can't actually just easily grab 1,000 or 1,000,000 examples of a porphyry copper deposit. And so when you try to apply this in a greenfields exploration or even a brownfields where you have a knowingly data poor environment, what happens is you can have an amazing algorithm that you can, let's say it trained on dozens of deposits. Well, what does it look like? So it produces maybe a prospectivity map, and you send your geologists to the field, and they collect some samples. And you take those samples and you get it back from the lab, and they have good, not great copper assays. And your algorithm had said, this is where to go. So is it correct? Well, it's too early to tell. You can't really tell if it succeeded or failed. So let's say you go beyond that. You take a couple drill holes, and you got 3 drill holes and they're total duds. So now it feels simpler. Did it get it right or wrong? Well, again, as explorers, we know not necessarily. We can actually probably think of famous deposits around the world where they were discovered on the 300th drill hole. So 3 drill holes missing doesn't tell you you don't have a deposit. And that's one of the challenges because it's a perceptive task, it leaves you in a similar position that your brain leaves you when you try to explain how you knew it was a business card. So this is where, in these certain environments, we can leverage on knowledge-driven models. And the way we can do this is because there's decades of experience in engineering and mineral deposit research that we can rely on when the data is not set up to give us the same kind of information. And where does this leave us? Well, another example that we could imagine is a tailings dam failure. We're all familiar with what happened in Brazil the last couple of years. And when you have something that you can't explain, even if it's extremely successful, there's problems with that. And so if you have a scenario where you've got an algorithm, a perceptive algorithm, that has studied every tailings dam in the world, and it tells you that there's a 7% chance of failure, well, if the dam fails, you cannot, the explanation, the robot said it was only 7%, is acceptable to absolutely no one. And it's one of the ways that we need to try to combine these techniques. And so, if we look at different applications in mining, by leveraging the extreme power of these perceptive tasks, which are quick, can be extremely accurate, but unfortunately cannot be explained, with different applications of sort of knowledge-driven models, you can actually come up with very robust, accurate predictions that then can be explained to important stakeholders. So how I'm going to demonstrate that is I want you all to think about this Russian 60s military ID again. Take a moment, bring it back into your head, and I'm going to show you, and I want you to tell me how you think you did. So, the question is, does this look exotic and completely strange to all of you? Or are there lots of aspects of this identification card that you could probably explain look fairly familiar? I mentioned it was a military ID. I mentioned it was 60s era. So you probably all would have been surprised if it was laminated in bright colors. Whereas you could perhaps made a guess, an informed guess that the photo would be in black and white because it was in the 60s. And you probably could have guessed that there were some hammer and sickle symbols. You probably could have taken a guess that it would have been written in Russian. And this is you leveraging both what you know about identification cards, right? What you can think about what you know, and then you can also think about, well, I can reason with time, I can think of different eras, and with all of these together, you can make a prediction on an object that you've never seen, that you certainly have never used, and if you were to explain to somebody, or if I had you draw it in advance, you probably would have been able to do a decent job of explaining your reasoning. And so, what I want you to do is not view any of these processes as something that's in opposition. Humans, we move back and forth between the perceptive and the cognitive all the time. And a good example of that is something like chess. If any of you have learned chess, you remember when you first learned it, it was a heavily cognitive task. You had to think about each move. You had to think about each piece and what it can do and where it can move. But as you get better, and certainly with grandmasters, they don't actually think about their moves. They see the board, they see a pattern, and they know what the implications of that pattern are, and they make a decision. And this is something that I think we can start to bring to mining, where we need to evaluate each of these tasks that we're doing. We need to evaluate whether or not the successes and failures in the data supports a primarily perceptive type of solution, or a more cognitive solution, or a mix of both. So what I'm hoping you can go back to your jobs at the start of next week and start thinking about some of the tasks that you do at work and try to decide which ones feel like more perceptive tasks to you and which ones are more cognitive, and perhaps which ones could do well with a bit of both. Thanks.